Hello students, welcome back to the second part of this video. So students, in the first video, I have done one simple mistake, like in shifting the terms, I put the positive sign. But here, when we shift the terms, we will get a negative sign over here. Okay, so let's repeat this step. Yeah. So here you can see this is the first equation that we have got after the differentiation of v with respect to first coefficient, that is CA. Okay. So here on the left hand side you can see we have two terms having CA and CB. Similarly on the right hand side we have two terms having CA and CB. Okay. So we will keep the right hand side term here. Okay. And we will shift the term from left hand side over here. So it will give the negative sign. Okay. Similarly, we will keep this second term of the right hand side on the same side here, and we will shift this term over here. That will give the negative sign. And this whole equal to 0. Now you can see in this first term CA is common. So we are left with, in the bracket, HAA minus E SAA. Okay. Similarly here, CB is common. HAB minus E. Here we have okay. So now we have, you can see this is the first equation that we have derived. Okay, now what we will do, we similarly in the same, by following the same method, we will differentiate curl E. We will differentiate E with respect to CB. Okay, again, we will put it equal to 0 and we will get a second type of equation. And that equation will be equal to, here I will directly write the equation. Okay. There is no need to do the differentiation again. Okay, so I will write the direct equation, direct result I'm writing here. So you will get the second equation after solving this. You will get CA H BA minus E SBA and plus CB. The coefficient of CB will be HBB minus ESBB. Okay, so this is the first third equation, and this is the fourth equation that you will get after differentiating E with respect to CB. Now we have derived two equations. Okay, now these two equations are equal to 0. These two equations are equal to 0. Okay, so from these two equations we can generate one determinant. Okay, so that determinant is equal to, how we can write the determinant? So the coefficient of CA and CB can be written as the elements of determinant. Okay, for example, like here I will write one determinant over here. So the first term of the first equation, this one, HAA minus ESAA will be the first element of the determinant. So the determinant is equal to HAA minus ESAA. Okay, similarly the second term we will write, HAB minus ESAB. Okay, now this term will be the next element, HBA minus ESBA, and this will be the last element, HBB minus ESBB. Okay, and this determinant equal to 0. Now this determinant is very important, and this is known as secular determinant. Okay, because this determinant is formed from secular equation. These two equations, third and fourth, these equations are known as secular equations. Okay, this is secular determinant. Right? So now we will see how to solve this secular determinant for getting the energy value. But before that, we will see in this whole derivation there exist three types of integral. Okay, now these integrals. So let me write over here. So here three different kind of integrals are present. Three different integrals are present. Okay, first integral is known as Coulomb integral. Coulomb integral. Right? And second integral is known as exchange integral. Exchange integral. And third integral is known as overlap integral. Third integral is known as overlap integral. Okay. So what is Coulomb integral? So Coulomb integral is of type HII. Okay, and exchange integral it is of type HIJ. And overlap integral is of type SIJ. Okay, or SII. So here I may be equal to J or I may not be equal to J. Right? So this HII, it represents the Coulomb integral. Okay, which is equal to integration of psi I H psi I. In this derivation, this is equal to HAA or HAB. HAA or HBB. Okay, so same nuclei are present here. So this is this integral, it represent these represent the energies. Okay, because here we have energy operator, so it represent the energy. So it represent energy of electron which is present in atomic orbital of atom I. If it is HAA, that represent energy of electron in A orbital, A atomic orbital. Okay, and if it is HBB, it represents energy of electron in atomic orbital of second nuclei. And the second integral is exchange integral. In exchange integral, yes. So here exchange integral is represented by integration of psi I H psi J d2. Okay, now this integral also represent energy. So it represents the energy of interaction. Energy of interactions. Interaction of electron. Interaction of electron with nuclei A and B. With nuclei A and B. Okay. Third type is known as overlap integral. So overlap integral, it is represented as psi I psi j. Okay. If I is equal to j, then this integral becomes, if I is equal to j, then this integral becomes psi I or psi j. If it is not equal, then it will be psi I psi j. Okay. So student psi, when I is equal to j, okay, it represents psi I into phi as phi, it's phi. Phi I and phi A, that means phi I whole square. And you know atomic orbitals, these are normalized, so the value will be 1. Okay, similarly here psi square j is equal to 1. Means in this derivation, we are writing SAA or SBB. So SAA and SBB, because these are same nuclei, so value will be 1. But in case of SAB, in case of SAB, okay, in case of SAB or SBA, these we write equals to 1. Sorry, not equal to 1. This we write equals to S. Okay, because these integral will be having some value. So this is known as overlap integral. Okay, now one thing more that I want to discuss here, that we are explaining the LCAO method for hydrogen molecular ion, right? So in hydrogen molecular ion, both the nuclei are same, either it A or B, but both are same, right? So in this case, for the same, like for homonuclear molecules, in which both the atoms are same, in that case, HAB equals to HBA, okay? And sorry, HAA equals to HBB because both nuclei are same, okay? And this SAB equals to SBA, which is equal to S, right? So we will use these results in the determinant. Okay, we will use these results in the determinant to solve that determinant. Okay, now in place of HAAB, in place of HBA, we will write HAB. In place of HBB, we will write HAA. So let's see the determinant, how it will be written now. So I know the elements of this determinant. So first element was HAA. So HAB minus E. Okay, this is HAA. HAA minus E. And because AA is 1. And the second term is HAB minus ES. Okay. And third term here, HAB minus ES. And here, H11 minus E. So in this way, we can write the determinant. So now we will solve it. How to solve? Just this by cross multiplying the elements. Okay, just cross multiply the elements. You will get the result. So we will cross multiply. Here you can see the first term and this last term. Okay, first and fourth both are same. Na? So in this way we will cross multiply these terms. So here we will write H11 minus E whole square minus HAB minus ES whole square equal to 0. Now this is like A square minus B square. Okay, so here we will use the identity. A square minus B square is equal to A minus B and A plus B. Okay, so this is my A and this is B. So I'll write A minus B and A plus B. H11 minus E plus this represent HAA now. Plus HAB minus ES. Okay, so this is A plus B. Now write A minus B. HAA minus E minus HAB plus ES equal to 0. Okay, now you can see the product of these two terms equals to 0. Now either this will be 0 or this will be 0. Okay, now you can write this. Now you can write the first term, that is HAA minus E plus HAB minus ES equal to 0, or HAA minus E minus HAB plus ES equal to 0. Okay, after solving this, you will get the values of energy. Let's find out the value of energy. So here you can see, here also we have E, here also we have E. That is common. Okay, so I can write it as E 1 plus S. Okay, 1 plus S. Now value of E, here it is equal to, the value of E equals to HAA plus HAB divided by 1 plus S. Similarly, from here we will get the value of energy, that is equal to Here I am directly writing the result. So this is equal to HAA minus HAB 1 minus S. Okay, so we are getting two energies. So this value of energy corresponds to the energy of the bonding orbital, which is represented by E plus, and this is this represent energy of anti-bonding molecular orbital, which is represented by E negative. Okay, so here we have derived the formula for energy using the variation principle in linear combination of atomic orbital method for that we are using for H2 plus ion. Okay. Similarly, we can write the value of the wave function. Okay. So in order to write the expression for the wave function, we need C1 and C. We need the value of CA and CB. Okay, because the wave function psi, it is equal to CA phi A plus CB phi B. Okay, so in order to write the wave function, we need to know what is CA and what is CB. Now, how to find CA and CB? Okay, to find CA and CB, we will use E plus and E minus values, means the value of energy, in equation number 3 and equation number 4. Okay, that we had written earlier. Equation number 3 and equation number 4, like here. Yeah, this equation number 3. So in equation number 3, we can use the value of energy. Okay, we can put the value of energy in order to get the value of CA and CB. Okay, so here when you put the value of energy here in this third equation in place of E, when you put the value of energy, which is equal to HAA plus HAB upon 1 plus S. Okay, when you put this value in this equation, third equation, then you will get CA equals to CB. Okay, and when you put the value of E minus, the second expression, in fourth equation, then you will get CA is equal to minus CB. Okay, so we are getting two values here. So when you use the energy expression, okay, in equation number 3, then you get CA is equal to CB. Okay, CA equal to CB. So I can write it equal to C. Okay, then your wave function, that is psi plus, which is for bonding orbital. It is, the general expression for psi, it is CA phi A plus CB phi B. Now CA and CB both are equal, so that is equal to C only. So the wave function for psi plus, it is phi A plus phi B. Okay, similarly psi minus will be equal to C phi A minus phi B. Okay, because when we put the value of energy for antibonding molecular orbital in fourth equation, then you get CA equals to minus CB. Okay, so these two values of psi plus and psi minus we get. Okay, now further you can normalize it. Okay, we know the condition for the normalization. Both the wave function can be normalized. Okay, in order to get the value of C. So that part, please try to do by yourself. Okay, so here we have completed the second part of a linear combination of atomic orbital for hydrogen molecular ion. So next thing, that is the normalization part, that you can do by yourself. Okay, now from my side, this topic is completed. Thank you so much for watching.